Alright guys, we're going to make a quick little video here to talk about compound interest, and the reason we're doing that within an exponential unit is, as you'll see here in this first one, we're going to have numbers that theoretically could be raised to variable powers or variables raised to number powers. You'll see that we're using an exponential, the number e, in our continuously compounded interest formula as well. Okay, so let's define this formula. So that a of t, that's going to be the ending balance, and we're thinking dollars here, where t is time. Okay, at the end of so many years or days or months or hours, okay, whatever the time is given to us. Okay, the ending balance after some sort of time. The a sub 0, or also known as a naught, okay, you'll learn about that in statistics if you take it. That's going to be our initial balance or investment. Okay, so basically the money we're starting with. R is going to be our rate. Okay, that would be traditionally an interest rate, a percentage, also known as an APR, an annual percentage rate. Okay, T is going to be time. Okay, and we're going to talk about this compounded word. Okay, the N in the formula will be how many times per year the investment compounds. Basically, this will tell you how often the investment will earn interest. Okay. Big thing here is that the N and the T, they have to match in terms of the unit of time. Okay? The N and the T have to match in terms of unit of time. Okay? So if T happened to be in days, we would either have to maybe convert that to years, or we'd have to convert N to days. Okay. And the examples of terminology for T, or for N, in terms of what we're going to plug in, if we were compounding monthly, that would be, N would be 12. Okay, how many times per year the investment compounds. If we're compounding quarterly, every quarter N would equal 4. Compounding semi-annually, N would be 2. Semi-annual would be twice per year. Okay, just some different things to show you there. Okay. Now, continually compounded interest is where we're going to use that number E, that exponential number. Okay. Continuously compounded interest doesn't really actually happen for the most part in the real world. We will get back to this formula later in the chapter when we're talking about exponential growth and decay. All right. If you can find a bank to give you continuously compounded interest, that would be awesome. It doesn't exist. Okay. But we study it nonetheless, and again, it's going to be more applicable to real world stuff when we get to the end of our chapter and talk about bacteria and population and other exponential type models. Okay, but similar to the first, this would be kind of like our ending. Okay, our ending value. This would be our starting value. Maybe it's dollars. Later in the chapter, it might be a population. Okay, E is E, and then our R, our rate, and our T, our time. Okay, so we got our rate, our time, our initial value. Initial. Okay. We're just going to do one quick example together on this notes page, and then we'll get into a worksheet in class. We're going to have some fun with these compound interest type problems. So here's something that it might look like. It says, suppose you invest $100 at 5% interest. Calculate the amount you would have after 1 year if the interest is compounded semi-annually, quarterly, or continuously. Okay. All right, semi-annually, let's think N equals 2. Quarterly, we're going to think N equals 4. Continuously, we're going to think we need to use that formula that has E in it. Okay. All right. So A sub T for this first one should equal 100. There's our initial investment, $100. Okay. times 1 plus 0.05, that's how we write 5% into a formula as a decimal, over n, the number of times per year it's compounding, here would be 2, and then to the n times t, okay? So that would be 2 times, it says 1 year. I'll pause there, let that sink in for a second, and then we'll do some calculating. If we do type this in very carefully to our calculator, making sure our order of operations with our calculator would be fine, we're going to get 105.06. For quarterly, same information, 100, 1 plus, same rate, but we're compounding 4 times per year. N is 4, we'll go 4 times 1. And it looks like if it was compounded quarterly as opposed to semi-annually, if our calculator is right, we would earn an extra 3 cents on our money. And if it was compounded continuously, that's where we're going to want to use this formula here with the E, our continuously compounded formula. 100 times E to the 0.05 times 1 formula. And it should make a lot of sense that if we were compounding our money continuously, we're going to earn a little bit more. 105.13, an extra 4 cents, okay? So when money compounds, okay, when they take the interest into consideration more times, it would make sense that we would be earning more interest. So continuously earning more interest, $5.13 over that year, then quarterly, $5.09, then semi-annually, $5.06. If it didn't compound at all like a normal investment account or savings account and we were earning 5% interest, obviously we would just earn $5 that year because 5% of 100 is $5. All right, that's it for this video.